Okay, what we're going to discuss in this talk tonight, what is a prism, adding and subtracting prisms, splitting prisms, Prentice's equation, and prismatic effect. Now, before we get to prismatic effect, you've got to understand the basics of prism, what a prism is, what it does, how to add and subtract prisms. Now, you may be asking the question, why do we have to know how to add and subtract? Well, this is when it comes to prescribing lenses where, let's say, your scripts are not quite the same. And when you start rotating your eyes, you're going to start incorporating prismatic effect. And you'll find the one eye might incorporate X amount and the left eye Y amount. So you've got to know, are you increasing the prismatic effect or are you decreasing? So that's pretty straightforward, but we've got to know the basics first before we get into the prismatic effect when it comes to spectacle lenses. Splitting prisms, the same thing. Usually if you need prism in a pair of glasses and the prism is quite high, so instead of putting all the prism in one eye, what we'll do is we normally split it. We normally split them equally. Prentice's equation is an equation we use to calculate the prismatic effect at any point in a lens, or for that matter, in a pair of spectacles. And of course, prismatic effect, that will be the effect of the prism when it's incorporated into the lens. Right. Now, just to explain what a prism is, a prism, as you can see over here, I'm just showing you this in 2 dimensions. It's got an apex and it's got a base. Now, your base obviously is your thicker part. Your apex is your thinner part. And we normally determine the power of a prism, the deviating power, by the apical angle over here. Now, if you had to look through a prism, and this is a plane prism, it's not a refracting power. In other words, it's just deviating. So if you place an object at the point where I'm pointing now, and if you're viewing it from the other side of the prism, you will not see that object in its exact spot. It's going to be deviated towards or displaced towards the apex. And other than displacing objects, prism also splits white light into its different colors. Now, you may be asking now, so how does that affect spectacle lenses? It affects spectacle lenses in a large way, especially when your scripts are high and you're looking more towards the periphery, because the further you look away from the optical center, the greater the prismatic effect and the greater your angular dispersion. But we will get into that once we've discussed the basics. Okay. Now, when we talk about a prism or one prism diopter, in other words, a prism with a deviating angle of 1 prism diopter, it will displace the image of an object 1 centimeter, which is y over here, over a distance of 1 meter. Now, if we look at the equation over here, we can see that P over 100 is equal to y over x. Now, P over here is basically your displacement, which is y. Over 100 is equal to y over x. And we can, just by rearranging these equations, y is equal to 100 tan d, P is equal to 100 tan d. And what you'll find with rearranging these equations, 1 prism diopter is equivalent to 0.572 degrees. So this applies whether it's a pure prism or even when it's incorporated into a prescription. Now, in order to calculate what the prism is, there are different ways of doing it. Now, we're doing it the old-fashioned way. Now, of course, the modern way is stick it on a vert and you can see exactly where your displacement is if it's not in the center of your target, of your graticule. But now for us old school people, we're a bit technologically disadvantaged. We use the old style, where we use what we call a tangent scale. In other words, what we do is we can place a ruler at a distance of 1 meter away, and we will place a prism in front of our eyes with the apex directed along the ruler. So if you to now look at the 0 point on the ruler, you look slightly above the prism and then you look through the prism. And while you're looking through, in other words, you're going to get like double vision. You see where that 0 is displaced. Now, in this example over here, by looking at it through the prism and slightly above, you'll see that this 0 is displaced towards the 3. And if you're 1 meter away from the ruler, this prism would be a 3-prism diopter prism. So this is the old-fashioned way of doing it. Now, you may find if you're out in the bush somewhere and you want to calculate what the power of a prism you have, this is an easy way of doing it. That's if you don't have a bird with you. Right. Now we talk about prism orientations. Now, there are different ways of doing it. There are different ways of how people write their scripts out. Now, let's take 2 circles over here. This will be for the right eye, and we've got the left eye over here. If we had to split this up into 4 quadrants, now for the right eye, quadrant number 1 would be, if it's along the horizontal, now you can see in this, the prism is directed towards the nose or nasal. In other words, when we talk about prism, we always talk about the base direction, never ever the apex. It's always the base direction. So if it's placed exactly along the horizontal towards the nose, that would be base in. And this first quadrant, if this prism has to be displaced anywhere in this first quadrant, it's going to be up and it will be in. And if it's directly in the vertical, it will be base up. In the third quadrant over here, you can see it will be up and out. Along the horizontal, you can see it will just be out. Now, if you're going to the third quadrant here for the right eye, you can see now it's down and out. And along the vertical over here, it will be down. And in the fourth quadrant, it's down and in. When you compare this to the left eye, quadrant number 1 here is up and out, whereas for the right eye, quadrant number 1 would be up and in. And along the horizontal over there, you can see that would be base out. Up would be base up as usual. Now, quadrant number 3 for a left eye would be up and in. If you compared that to your right eye, quadrant number 3 is up and out. And along the horizontal towards the nose, that would be base in. And if it's in the third quadrant, in other words, you're placing that the base in the third quadrant, it will be down and in. And fourth quadrant, down and out. Whereas the fourth quadrant for the right eye is down and in. So now this is where sometimes, depending on how you write your base directions, it can be a bit confusing. Because I know what some people like doing is, let's take an example over here. When you do an axis for astigmatism, you place your right eye and your left eye together as I've drawn over here. Naught would be where I'm pointing, which is more nasal. Naught for the left eye would also be, but now on the temporal side. And then when it comes to axes, we work like with half the protractor, which only goes up to 180. So 0 and 180 will be the same. Same thing applies for the left eye. 0 and 180, obviously, for axes is going to be the same. But when it comes to prism, 0 and 180 is completely opposite. So if I want, for example, base in prism, it will be by the 0. And in the case over here, 0 over here is going to be base out. But either way, 0 and 180 are both the same. It's just a case of getting your base direction correct. Now, for example, if a prism of 4 diopters is required for the right eye at 200 degrees, okay, now, if you notice, we are using the complete circle over here. But just for this, I'll explain to you exactly what I'm doing. At 200, what some people do is they would write this script out at 4 prism, out and down at 20. I don't know if there are any people here that do it like this. In other words, there you've got 20, and 20 over there obviously is going to be up and in. But if you write out and down at 20, so that means the base is in the opposite direction. Now, I know a lot of the old school used to write their prescriptions like this, and I'm not too sure if any of the new school do that. So in other words, I'm going to go back to you because I see Belinda's a bit confused.
No, I don't know how many people order at axis 200. I would think 180, 90, 0, out, in, up, down.
So no one gets the base out and down that you're aware of, that you've seen.
Few. Am I right or wrong?
It happens.
Yes.
Whether it's 1 or whether it's 100, it happens.
Yes.
So, and how do they write their scripts out? Do they write down and out at 20? Or would they use the full protractor?
They use the protractor.
So they'll say 200.
I would assume so, yes.
Okay. Well, let's say some practitioners will still use the old way by saying 4 prism, out and down at 20. But now this can be a bit confusing, especially when you're talking about the 20 degrees. Now, that's why I'm just saying now, I'm not sure how many practitioners you are listening here do it this way. But I know the old school, I'd say when I first started, this is how they used to write it. And if they wanted their prism, let's say, for example, at 20 degrees, then that's easy. It says up and in at 20, for example. So this can be quite confusing. Quadrants can be confusing, especially when it comes to base directions and degrees. So a prism up in for the right eye lies between 0 and 90 degrees, whereas for the left eye, it lies between 90 and 180. So all I'm saying is if you're not using this method and you're using the full protractor, well, then I think it's less confusing. So if we go over here now, for example, a 4 prism down and out at 45 required for the right eye. It would be easier and less complicated if it was just written at 4 prism at 225. So there's no confusion. You don't have to worry about up and out, down and in, or whatever.
I agree.
If you write the full degrees, there's no confusion. Now, as I mentioned early on, I'm not too sure how you people write your prescriptions, but doing it this way, using the full protractor, then there's no confusion. If you notice here, there's a slight mistake over here. I've got 325. So 270 plus 45 should be 315. Now, I was wanting to see if anyone here would have noticed it, but that should actually be 315. But anyway, that's not serious. So all I'm saying is when it comes to writing scripts out that prisms that are oblique, it's so much easier to write the actual degrees, use the full circle. Whereas when it comes to axis is only used between 0 and 180. Whereas when it comes to prism, and if there's less confusion, use the complete circle. So if I wanted prism down and in, I can say, right, for example, over here at 325, there's no doubt it's going to be down and in. So I thought I'd just mention that for... although many of you, I suppose, are using it like this, but I suppose do what makes it easier for you.
We only have actually 4 options to order.
And what's that?
Horizontal, out, in, up, down.
What about oblique?
That will be a special order.
Does your lab know how to do it?
Yes.
Oh, they do?
It's just a special order.
No, it shouldn't be special. It should be all the same. But anyway, I'm just saying, okay. So, but you do get prisms that are oblique. Yes, absolutely. Okay. If you're all happy with that, I can't see your questions now, but we'll continue. Okay. Right. Now it comes to adding and subtracting prisms. Now, it's also pretty straightforward. If you are adding and subtracting prisms, now we talk uniocular. That's one eye only. So a 2 prism down and a 3 prism down for, let's say, it's only one eye or just in isolation, your total prism over here is going to be -2. Now, where the -2 comes in, I use the minus sign here because it's down. If it was base up, I would use positive. And now if I'm taking a 2 down prism and I take another 3 down prism, your total prism over here is going to be 5 down, -5, which is down, which is pretty straightforward. There's no rocket science over there. Now, 2 prisms in contact with their bases in opposite directions, the total deviation is the difference in the 2 prisms. In other words, I've got a -2, which is down, and I've got a +4, which is base up. So in this case over here, it's going to be the difference, which is 2 base up. So this is straightforward. Nothing complicated about this. Now, let's take it now when it's binocular. Now we can add and subtract binocularly. Right. What we use over here, we use a Sine Convention. Now, if you can remember what a Sine Convention is, anything that's up is positive. Anything that is down, we refer to as negative. Anything directed towards the right is positive. Anything directed towards the left is negative. And we're going to use this Sine Convention when it comes to adding and subtracting prisms. Right, for example 1 over there. Let's say for the right eye here, we have 2 out. Now, as you can see, out over here, the prism is towards the left. So it's going to have a negative sign. And for the left eye, it's 5 prism out. Now, if you see over here, out for the left eye is directed towards the right. So it's going to have a positive sign. Now, if you wanted to calculate the difference, now when you add the 2 together, so your resultant is -2, as you can see, this is to the left, -5, which is positive. So your total prism over here for the right eye would be 7 PD out for the right eye. And now if you wanted to see what the prism was in the left eye, it would be 5, because it's to the right, -2, because this prism is to the left. So we're following the signs. And that also equals 7 out. So as you can see now, I'm sure you've noticed when you've prescribed prism, and if you want to split them or whatever, or you want to add the 2 together, if it's base out in the one eye and base out in the left eye, your total is going to be the same. You're going to add them together, so your total there is 7 out. Are we all clear on this? Now, in the case over here, now, all what I've done over here, I've just swapped them around here. We have now made the right eye 5 out, and I've made the left eye 2 out. We follow the same procedure, and you'll see over here now for the right eye over here, it's -7. In other words, -7, that's going to be out for the right. And for the left eye, we'll end up with a positive, which is 7 for the right. So in other words, all what we are doing over here, if you wanted to place everything in one eye, what would the total prism be? So in other words, 5 out and 2 out gives us 7 out. So we're just following the signs, and that's how we get our answer. Now, the same thing over here, what we are looking at here now is, for the right eye, we've got 5 prism in. So in other words, the prism is to the right, so it's going to be a positive value. In this case over here, this prism here is also to the right, okay? So it's also a positive value. So now what we're going to do over here to calculate what your resultant prism is, you got 5, which is positive, minus, now in this case over here, sorry, I think I've made a mistake over here, because your resultant is 5, -5, that there shouldn't, that minus over here shouldn't be there. But anyway, so it's going to be 5 minus 5, which is equal to 0. Now, you might be a bit confused over here when I say it's 0. How can this be 0? Because I've got a 5 there and I've got a 5 there. They're both more or less, when I say in the same direction, they're both placed in the same direction, which is right. Now, if you see over here, I've actually made a mistake over here, because if it's 5 minus minus, that's going to give me a plus. So in other words, it should be 10. Sorry, this minus over here, because it's to the right, it should be a positive value. So 5 minus 5 gives us 0. So now, in other words, your displacement is equal, okay? So in other words, there's going to be no visual discomfort. All what's going to happen over here, that the images are going to be displaced in the same direction, and there's no difference in the displacement. So there's no prismatic effect over here. Does that make sense? Does that make sense to you? Mm. If these were different, if these powers were different, which we'll see later on, then we got a difference, so there will be a prismatic effect. But if your displacement is the same, in the same direction, the one eye isn't fighting the other eye to focus. Your displacement is exactly the same. So although there's a displacement, an equal displacement with both eyes, there's no visual discomfort, and there's no prismatic effect. There's a difference between visual displacement and prismatic effect. So your prismatic effect here is going to be 0. As I've written there, there will be equal displacement in the same direction, however, no visual discomfort. Let's have a look over here now. Now we talk vertical prism over here. For the right eye, base down, which is 5 down, okay? And now because it's down, it's got a negative value. Left eye is also down, so it's going to have same direction, so it's also going to have a negative value. So if you want to calculate the resultant, I've got -5 minus 2, so that's going to give you a plus sign there. So your difference there is 3. Now, as you can see over here, there's unequal displacement. There's more displacement in the right eye than the left eye. So in other words, for your resultant, you got 5 plus 3, so you're going to be -3 down in the right eye, or alternatively, relative to the right eye, we're going to have 3 up in the left eye. Either way. But don't make the mistake of mixing up your directions, because if you mix your directions up, you're going to enhance the problem. So don't mix your directions up. So if I've got 5 down and I've got 2 down, your displacement's in the same direction. However, one displacement is slightly more than the other. So in other words, so what we are going to do, we're going to subtract the difference. So your resultant there is 3 down in the right. So in other words, relative to the left, I've got 3 down in the right, or relative to the right, I've got 3 up in the left. Okay, but this should be pretty straightforward for most of you. This is just simple adding and subtracting. But the same thing over here for the right. All what I've done now is I've just switched them around. So by switching them around, I've got 2 over here in the right, and I've got the 5 down in the left. So your resultant here is now going to be 3 up in the right, or alternatively, 3 down in the left. Whereas you can see now these differ from 8 and 9, they differ. Sorry about that. I've got a good operations manager over here. Right, let's take the right eye over here. There I've got 5 in, and here for the left eye, I've got 2 in. So following the signs, I did this first one over here. Now let's go to 4. Right eye over here is 2 in, as you can see. Left eye over here now is 5 in. So all what I've done over here, I've just reversed them. Well, I made the 7 in the left eye here. Right, so as you can see, that's still, you're still landing up with 7 base in because it's horizontal. Now, in the case of here, example 5, if I've got 5 in the right and I have 2 out in the left, now they're unequal. You can see they're unequal. So if we now do the calculation, you'll see a resultant for the right eye is 5 minus 2. So we got your resultant over here would be 3 in the right eye. Well, alternatively, it's going to be 3 out in the left eye. Just by following the signs over here. So 2 minus 5 is going to be minus 3, so it's going to be out. And for the right eye over here, 5 minus 2, which is 3. So here we're left with a positive. Positive is to the right. It will be 3 in for the right eye. Does this make sense to you, what I'm saying?
Yeah, it's maths.
It's arithmetic.
Yes.
This is high-powered second-year mathematics. Right, that's why you need math to do optometry. Right, let's look at 6 over here, where I have 6, but 5 out in the left. And over here for the left eye, I have 5 in. Now, what do you notice over there? 5 out and 5 in. These are equal displacements. So that means your difference is going to be 0. So there's no prismatic effect, only a displacement, but equal displacements in both eyes. So there's no prismatic effect as such. Okay.
My skills.
Now, you might be asking, how is this going to affect you? But you'll see by knowing how to add and subtract, when it comes to prescriptions, then it all makes sense. Right, now I haven't done this. Right, now we're talking vertical. Now you can see over here for the right eye, I've got 2 up. For the left eye, I have 2 up. They're both in the same direction. So that means your displacements are going to be equal. So in other words, your displacement is going to be down. The image will be displaced downwards. But if you do the calculation over here, you can see here now, resultant is 2 minus 2 is 0. So in other words, although there's a displacement, there's no prismatic effect. Now, when we talk about prismatic effect, what I mean by prismatic effect is when there's a difference in the two. So equal displacements, there's no prismatic effect. Right, let's look at 12 over here. Now, what do we have here? I've got 2 down in the right eye, and now I have 5 up in the left eye. So now let's do the calculation. You can see here, for the right eye is minus 2 minus 5, because 5 is positive, is up. Your total prism over here is 7 down in the right. So relative to the left eye, which means there's no prism in the left eye, I have 7 down in the right. Well, alternatively, I've got 7 base up in the left eye. So just remember, don't mix these up. If you're going to do your, if you only put all the prism in the one eye, for example, you can't mix them up. Otherwise, you're just going to enhance the problem more. So when they're in opposite directions, when it's vertical, you add the two. And if they're in the same direction, you subtract. Right. Those things all sorted. Okay. Right, let's do number 13 over here. What I have here, right eye, I've got 5 down. Left eye, I've got 2 up. So there again, I've done the same thing. I've just switched them around. And your resultant over there is 7 down in the right. And it's alternatively 7 up in the left. Whereas if you, I'm just looking over here. This is 5 down there, and I've got 2 up. So your resultant there is minus 5 plus 2, which is going to be minus 7. That's going to be down in the right, or alternatively 7 up in the left. Yeah. So there we are. So it's always good just to follow your signs. If they're in opposite directions for the vertical, you are going to add them. Now, this is just explaining to you what I explained earlier on. In a case like this over here, when light enters a prism, as you can see from below, it's going up. That's your blue line. After refraction, light is always going to bend towards the base. It's going to bend towards the base. That's of your prism. And the image is always displaced towards apex. So you can see over here, these images are displaced, in this case, to the patient's left. Now, they are both displaced in the same direction, which is, in this case, to the right from the front. Now, equal prism placed in the same direction displaces the image equally in the same direction. No displacement.
No discomfort.
Sorry, no discomfort. Sorry, no discomfort. As you can see.
There's a displacement.
There's a displacement, but no visual discomfort. Now, in the case over here, light enters the prism over here from your blue lines. I've just drawn this the other way around. If there are equal displacements, but no visual discomfort. Now, I'm just re-explaining what I've done already. Now, you can see over here in a case like that, if both prisms in this case are based down and the prisms are equal, you got equal displacement upwards. So there's no prismatic effect. There's equal displacement. In other words, one eye isn't fighting the other eye for fusion. And the same thing applies over here if it's based down. Equal displacement, there's no prismatic effect. So that's pretty straightforward. Okay, now in a case like this, where you've got a base down in the one eye and a base up in the other, you've got unequal displacements. Your right eye will displace the image upwards, left eye will displace the image downwards. You have to add the prisms together, and you can see you land up with double vision. You're going to have two images. So that's pretty straightforward.
You will have discomfort.
Definitely. Double vision. Right. Splitting prisms. Now, you must just remember, this is all Dispensing 201. I'm sure most of you have done this. You've done this before. And when it comes to splitting prisms, I'm going to go through this pretty quickly. So just to show you that it's more of a refresher for those of you who have forgotten. And for those of you who have never done it, you'll learn something. All right. So now it's common to split the prisms equally between the lenses. Now consider the following prescription. Right eye +1. Okay, left eye here is also +1. And now I need 6 prism base in. Now, can you imagine if you place all that prism in the one eye, the right eye will be thick in the nasal direction while the left eye will be thin. So for cosmetic purposes, we split the prism between the two eyes. This will balance the weight and cosmesis of the spectacle. So the script here will now read right eye +1, 3 in, left eye +1, 3 in. Now you can see it's in the same direction. And if we had to do the calculation, to work out to either eye 6 base in. 6 base in for the right or 6 base in for the left. Now the same will apply if the horizontal and vertical prisms are unequal. Now consider the following 7 prescriptions. We now want to split them equally. Okay. I've got a 4 in and a 3 up, a 3 in and a 2 down. Now, you must just remember, it's unlikely that you are going to test a patient where you're going to find prisms like this. It's unlikely. Normally, you'll find a deviation in the one eye only. But this is more of an exercise just to explain to you how we split them. Number 2, 4 out, 4 down, 2 out, 2 down. And I've got quite a few over here. Now, when we split them, you might have a bit of homework to do there. So work this out. I do have answers here that I'm going to show you. Just work them out and see if you're going to get the same answers I do. Oblique? These are oblique, yes. These are, you got up, You got 4 in, 3 up. So yes, that's oblique. Both of them are oblique. But now we want to split them equally.
Oh.
Vertical and horizontal. Okay. So those of you who are battling to do this, I'll do one example over here for you. I've got 4 in and I've got 3 in. Can you see that? Mm-hmm. So what's the total prism? The total there is going to be 7. I've got 3 up and I've got 2 down. What's the total? 3 up and 2 down. Opposite. Your total is going to be?
1 up.
No. No. 5. 5. They're in opposite directions. Up and down. So they're in opposite directions. So total here we're going to add. So what we have over here, we got 5 up total, and over here we got 7 in total. Now the rest is simple. Now we're going to halve it equally. So if I got 7 in, now we want to split it equally. Right arm will be 3.5 in, left arm will be 3.5 in. In this case over here, I've got 3 up and I've got 2 down. Total is 5. Now I want to split them. What's the half of 5? 2.5. So I'll have 2.5 up in the right, 2.5 down in the left. Gives me 5. You got that?
I've got it.
Right, now if you look at these other examples over here, I've left them like this to see if you can work them out yourself. And I've got 3 other examples over here, over there.
The answers.
Right? No, these aren't the answers. The next one's the answers. No, go back.
Oh, these are more.
Yeah, these are more over here. So 3 out, 4 up, 2 in, 1 up. 1 is just 6 base up, nothing in the left eye. And F is 6 out, and G is 6 down.
So the people are answering in the chat.
Are they answering? Okay, I've got the answers here.
Okay.
So I just want to see if you're going to pass the maths.
I don't think I
will. Okay, right. These are your answers over here. Just split them equally. Right eye was 3 prism diopters in, 2.5 up. Left eye 3.5 in, 2.5 down. So you can see they split equally. 2.5, 2.5, 3.5, 3.5. They split equally. Left B, 3 base out. Left eye also 3 base out. They split equally because the total there was 6. 1 base down, 1 base up.
But now in practice, Anthony, when you test a patient, you get the full one and then you
split it.
You split it. So it's the other way around.
No, that's why I said to you, it's unlikely that you are going to test a patient like this. But this is an exercise to see if you know how to split. Okay. That's all what this is. Now, well, what you're going to find, okay, these are also just split, where right eye half PD in, half prism in, 0.5 down, 0.5 up. You can see they're equally split. Can you see that? Yes. They're split equally. All of these are split equally. So if you can see here, okay, you've done this one here, 0.5 out, 0.5 out. Your total over there is 1 out. But if you're splitting, half. Okay, yeah. And over here, 1.5 up, 1.5 down. Your total over there was 3. Can you see that?
Yes.
Now we come over here, E. I think for E, the total was 6 up. Now we want to split it. The half of 6 is 3. So 3 up there, 3 down there. And the same thing over here, we had a total of 6 out. We halve it. 3 out for the right, 3 out for the right, and 3 out for the left total. So all what we are doing over here, we're just doing a little exercise as to how to split these things equally. Now, I've got some examples later on where we'll see how we can split normal prisms equally. So this is just a little exercise.
It's maths.
Arithmetic.
Yeah.
Arithmetic. In fact, it's what metric math do you do? Not the
trigonometry. This is not trigonometry.
No. It's the easy
geometry.
No, the easy maths. They call it easy maths. In other words, the maths that's not university entrance. What do you call it?
I don't know.
Okay. Right. Here's an example over here now. We're going to test over here as to, now I'm sure many people are aware of this. We now have a situation where the right eye now, this is a genuine situation now. Right eye, no prism. Okay. Left eye, you can see there's a deviation here. There's a squint, it's a strap. And this strap happens to be 4 prism. Now, is it based in, out, up, or down?
Let's wait for a few people to answer in the chat.
Okay.
Before I...
Yeah.
Let's see. In the chat...
Math, that's
thank you, Tsitsi.
That is what I was looking for, yeah. That's what I was looking for.
A lot of people said maths literacy.
Okay.
Okay, who's got an answer there? Base out. Are they all correct?
Right, base out. I'll just go off the screen. Let's see. Yes, you would need base out. You would need base out.
Clever people are listening.
Right. Now, let's just see now. Now, I know everyone here is qualified, so they should get this right.
Okay.
But, you know, when you talk to students, they seem to think, no, you can't put base out, you must put base in, because what you want to do is you want to straighten that eye. Go back one, I think you've gone. I did the next slide. Okay. So now, if you had to put base in, what's going to happen?
The image is going to go.
No, that eye will turn straight. But what's going to happen to that eye?
Oh, my goodness.
Your eyes work together. Your eyes work together. So if this eye is going to go in, that eye is going to come straight, that eye is going to go in. Can you see that? But I know coming from qualified optometrists, you know that. But that would happen if you had to put base in. So we need base out. Now, where are we?
This is the correct one. You're putting base out in front of
the eye.
Yes, right.
Now, if I put the full prism over here, I've got base out, right? So that means there'll be no prism in the right eye, but I've got 4 prism base out in the left. But what have we just been doing? We've been splitting the prism.
Okay, yes.
Now, people are going to say, but listen, why do you want to put prism in the good eye? Surely it's going to affect the way you see.
Cosmetics.
We're doing this for cosmetics. Right, so with the full prism, go on back again.
No, this is the next one.
Oh, that's the next one. So what we do over here, we split it. We only put 2 out in this over here. We need 4, but we're only going to put 2 here. So in other words, light coming in will focus not quite where it should focus. It's going to focus. In fact, there's 2 little prism over here. Can you see that?
Yes.
So that's not good enough. So now we have to put the prism in the right eye also now. Change the slide there. Right, so by changing it now, so what we do over here now is we've now put a base out. This is we just split the prism 2. So now light's going to come in this eye and it's going to bend there and miss the macula. Can you see that? So what's going to happen now? The right eye is now going to change the slide. Next. Both eyes are going to rotate to the left. Next one. So that means now the right eye is rotated to where the light is focusing, which was 2. The eye over here where we had 2 little prisms. Because that eye is rotating, this eye is going to rotate 2 also. And light will focus on the macula. So there we can see macula to macula. That's how we split. So now I've often had the question, okay, a lot of them come from students, obviously, but now you're affecting the good eye.
So it's still back in the right answer.
Yeah. So they are right. So you split it, it's 2. Now, if we look over here, you can see over here now is if you got base out in both eyes for a person that does not need prism, what's going to happen? Light will come in, it will bend towards the base. So that means image is going to be displaced inwards. So that means this eye is now going to converge more.
Yes.
So as you can see over there, if the eye was reading at object O, because you've now got base out prism, it will deviate, displace that object closer. So that means you're going to have to converge more. And if you look at base out is exactly the opposite, where light will bend and it's going to push the image outwards. But now if it's for someone who maybe has got a bit of convergence insufficiency, you can give base in prism over here. So in other words, there's your object. Now because of the base in, it's going to push that image out slightly, so you won't have to converge as much.
And this is what we do for our Marpilux Max, for your EXO people. If you give them a high add, you add base in to make the reading more comfortable.
But you don't have to, because the lens has base in already when they're looking through the reading.
But not enough.
Well, it depends on what your inset is.
It depends on what your foray is.
Yeah. Right, are you all happy with this? Right, spectacles and prism. Right. Now, this is something I'm sure you're all familiar with. Now, we've been talking about pure prisms. Prisms with no refracting power. Now, all what we are doing over here now, we're incorporating prism into a lens. Well, we're not incorporating it, it just happens to be there. If you take light passing through the optical center, it's going to go straight through undeviated. Now, as you move away from the optical center through a lens, you're going to get refraction. As we move further away, light coming in further away from the optical center, it's going to refract even more. And on the periphery, it's going to refract even more. So in other words, you can see here, D3 is less than D2, D2 is less than D1. So in other words, on the periphery, there's more deviation. So in other words, what we can say here now that a lens is a combination of prisms with increasing apical angles. Of course, there's a blend because your deviation is more the further away you move from the optical center. So in other words, each point that you're looking at through this lens, you're basically looking through a prism. You're looking through a prism. Now, let's look at the dotted line, the red dotted line. This is a pure prism. If light had to enter this prism, light would leave parallel. But with it being a lens, now a lens of positive power is thick in the center and thin on the edges, we can sort of say that it's a combination of two prisms, base to base, and increasing apical angles as we move away from the optical center. That's why the deviation on the edge is much greater than the deviation closer to the optical axis. And the lens of negative power is exactly the opposite. It's exactly the opposite. It's like a combination of two prisms, apex to apex. And with increasing apical angles as we move away from the optical center. As you can see, D1, the deviation is greater than D2, and D2 is greater than D3. So if you're not looking through the optical center, you are basically looking through a prism. Because I'm sure you've all done the transverse test when looking through a plus or a minus lens. You get a with movement or an against movement. It's basically a prism that you're looking for. Now, in order to calculate the prismatic effect, we use Prentice's equation, P is equal to CF. Are you all familiar with this?
No, it's good.
You're all familiar with Prentice's equation, where P is the power of the prism, C is the distance from reference point to the optical center, F is the power of the lens. This is what we use to calculate the prism at a point in the lens. Right, so what we do is now, for example, if we wish to find the prismatic effect of a +5 and a -5 lens at a point 5 millimeters below the optical center, we use Prentice's equation, P is equal to CF. Now, you must remember, C is measured in centimeters. Because with the prism, one prism displaces 1 centimeter over a distance of a meter, we incorporate C in terms of centimeters. Now, 5 millimeters happens to be 0.5 centimeters. So if you want to calculate the prismatic effect at a point on a plus lens or a minus lens, we're going to use Prentice, P is equal to CF. Now, here again, if you're going to use the maths or the simple arithmetic, we're going to follow signs, okay? So now, we are now going to look at a point on this lens 5 millimeters below the optical center, okay? So now, if we follow the Sine Convention, we are going from that point up to the optical center. So in other words, so that value is positive. So in other words, you can see over here, the 0.5 is positive. If the point of concern was above and going from that point downwards, that would be negative. So from the point of reference to the optical center is positive. So it will be 0.5 times the power of the lens is 2.5. So now we follow the sign. Now the power here is 2.5 prism diopters. Now you can see now it's positive. So if it's positive, positive is up, so it's going to be base up. But another way of doing it, if you want to start drawing pictures, draw your picture, look at that point where I'm pointing to now. If you had to imagine half this lens being a prism, there where I'm showing you now would be the base, and that would be the apex. Where is the base relative to that point? It is up. Same thing over here now. If you take a lens of negative power, it's 0.5 times minus 5, so we're left with a negative value, so it's 2.5 base down. Now the same thing applies. If I'm looking at that point where I'm pointing there now, where's the base relative to that point? It is base down. So if you want to follow signs or if you want to draw pictures, either way, whichever way you prefer. Another example, if you wish to find the prismatic effect of a 5 diopter minus 5 at a 0.5 millimeters to the right of the optical center, we use Prentice's equation again. So in this case now, it's 5 millimeters to the right. So here's my lens. The point over there is to the right. So we're going to measure from that point. Now we're measuring it to the left. So that's going to be negative. So it's negative 0.5 times 5, and it's negative 2.5. So it's base left. In other words, if it was the right eye, it would be base out. Can you see that? So over here, okay, I didn't say if it was a right eye or left eye, but anyway, it will be there, base left. So just to repeat, if it was the right eye, it would be base out. If it was the left eye, it would be base in. And the case of the negative 5, we do exactly the same. So from the point there to the optical center is negative. So it's negative 5 times negative 5, which is the power of the lens. So it works out to 2.5. Now, as you can see, it is positive. So if it was the right eye over here, it would be base in. If it was the left eye, it would be base out. So you always measure from point to optical center. I think it's it might be a bit tricky, but if you are familiar with it, it is pretty straightforward.
So this is just another example.
Oh, wait, no. This over here quickly. Now, find the prismatic effect of a point 10 millimeters and 2 in of an astigmatic lens. So now we have an astigmatic lens. Now you can imagine this being a lens, a toric lens with a cylinder. Now if you want to look down to read, what would the prismatic effect be at that point? So now it's 10 millimeters below, 2 millimeters nasally. So in a case like this, this could be a right eye because it's nasally. Now the power is plus 2 minus 4 axis 90. So now we break this up into vertical and horizontal components. So plus 2 minus 4 is plus 2 in the vertical. It will be negative 2 in the horizontal. And now we use P vertical. So it's 1 centimeter times 2, which is your power in the vertical. So it's going to be 2 prism base up And for the horizontal, it's 0.2 times -2 because the power is along the horizontal there. And it's 0.4 base in. So in other words, at that point over here where they are looking, it will be looking at 2 prism base up and 0.4 base in. And okay, this I've done before. Oh yeah. Okay, so what do you want to do?
I don't know how long it's for.
Okay, this question I asked at the last webinar we had, where we asked the difference of which lens gives a greater field of view. And you'll find that negative lenses give you a wider field of view compared to a positive. And this is all to do with prismatic effect again. Because if this is your object here for a plus lens, light will enter. After refraction, image displaced towards apex. So in other words, for the lens of positive power, is pushing that object out. And for the lens of negative power, if this is your object over here in black, light will come in and sort of bend towards the base. It's going to bring that object into your field. So that's why you'll end up with a different, a wider field. And okay, what I was going to do over here when it comes to anisometropia, isometropia, and antimetropia, I'm just discussing your field of view through your lens. So in a case like this with isotropia, right lens and left lens is +5. Your field of view is going to be probably the whole lens. You won't suffer any prismatic effect. In fact, you'll suffer displacement, but there won't be prismatic effect. Now, the same thing, if I now use Prentice's equation at a point 1 centimeter below, I'm going to land up with 5 prism up. For the left eye, it will also be 5 up, same direction, only displacement, no prismatic effect. Nearly finished. Now, in the case of anisometropia, now this is something very important. This is when it comes to interpreting a prescription. Now you've got a lens over here now where I've got a 5 diopter sphere and I've got a 2 diopter sphere. Now you can see it's anisometropia. So at 1 centimeter below the optical center by using Prentice, I've got 5 up, and for the left eye, I've got 2 up. Now your difference over there, we've got to subtract. So my resultant there will either be 3 base down or 3 base up for the right and left eyes respectively. So as you can see now, your field of view, this is the important thing to remember. Your field of view is pointless choosing a large frame if I'm only going to use that part of the lens. So always interpret your prescription. Okay. Now we have an astigmatic anisometropia. Right eye is -150 -4, left eye -050 -1. Now, break this into vertical and horizontal power cross. I've got -550 over there. I've only got -150 over there. So it's always important to check your script. An important thing to remember is check your axis. Check your axis. Because if this axis was both at 90, I wouldn't have that larger difference in the vertical. Now, as you can see over here, 550 in the vertical for the right, 150 for the vertical in the left. So what do we have? What's your difference in power over here? So I've got a 4 diopter difference in power. So if I'm looking at 1 centimeter below the optical center, I've got 5.5 prism. In this case over here, base down. And over here, I've only got 1.5. So now your prismatic effect is 4 prism diopters. So it's pointless choosing a large frame if I'm only going to use that part of the lens. So it's very important. This now, I mentioned this right in the beginning of the lecture. Everything to do with lenses is prism. Not only prescribed prism, but in cases like this. Next. Okay, and antimetropia, in fact, it's very much the same. It's exactly the opposite. So there, if you go down, I'm getting base down there, I'm getting base up over there.
Okay, it's the same thing.
And horizontal, this is the same thing again. We're looking at your field of views. Always look at your powers along the vertical. because your eye can tolerate less vertical prism compared to horizontal. Always interpret your script. +2, -4, +350, 150. Axis appears to be the same. Draw your power across. You can see you got a 4 diopter difference between the two. And okay, this is no. This over here is just a. In fact, this is my second last slide.
Okay. Right.
Now we've got a script over here. Consider the following prescription. Write out +4 - 2x is 180, +4 - 2x is 90. Okay, I don't know why I did this, but anyway, it's immaterial. The PD is 60. Okay. Now you send it to the lab and you find that the optical centers of the lenses are cut in at 70. So you are 10 millimeters out. What's the prismatic effect? Now we draw a power across. You got +2 in the vertical and +4 along the horizontal. And over here, I've got 4 in the vertical and 2 along the horizontal. Now, I'm 10 millimeters out, which is 5 millimeters in each eye. Now, using Prentice's equation along the horizontal, 0.5 times 4, I've got 2 prism out. Over here, for the left eye, I'm 1 prism out. So my total over here, because in this case over here, they're both out, we add. So your resultant is going to be the sum of the two, which is 3 prism base out. Now, I don't know if you people check your jobs or if you check your PDs, but this is very important when it comes to that. It's all to do with prism. Right, one more slide. Now, all what we are showing over here, for the right eye, I've got 2 out. This is equivalent to 2 prism out, and that there is equivalent to 1 out. So your total is 3. So it's always good to interpret your prescription before you start prescribing lenses. And of course, that's the last slide. So in fact, I went 15 minutes over time. I do apologize for that.